Okay, let's go ahead and get started. Sorry for the delay in starting class. I guess they had an exam, and I didn't feel like I could kick them out 10 minutes early. You should all write a letter to your congressman to complain about our unfair treatment and demand your money back. Okay. Okay, so today I want to continue with our discussion of the wave interpretation of elementary particles. So last time we saw that if we regard an electron as a wave, then there are really two important consequences that we can derive from this picture. So I remind you that we regarded an electron as a wave with a wavelength known as the de Broglie wavelength that depended on the momentum of the electron, just as the wavelength of light depends on the momentum of the photon that you're considering. And we saw that this would lead to two sorts of effects. Interference effects as of the sort that we already discussed in the double slit experiment, as well as a discretization of the allowed frequencies or the allowed wavelengths of an electron if you put it in some small region of space. So that's for an electron confined to a small region of space. In exactly the same way that if you take a guitar string that is infinite in length, you can pluck it and you will get arbitrary frequencies of waves propagating on that guitar string. But if you fix the endpoints of the guitar string, then you will only get certain allowed frequencies, the harmonics corresponding to that particular length of guitar string. So today I would like to make this picture a little bit more quantitative and see how it leads to a very interesting picture of atomic structure that was first understood by Bohr. So I'll be presenting to you the Bohr model, which I imagine that many of you have seen at least in some very elementary version. So I'll be fleshing that out a little bit more today and describing its relationship with the wave picture that we discussed last class, before using those insights that we have derived to dive into a more thorough and complete picture of quantum mechanics. So let us, before discussing the electron, let us recall the case of a wave on a string. Because I would like to make more quantitative this second statement that I have made about the discretization of the allowed frequencies. And so what I'd like us to remember is exactly how, for a wave on a string, the allowed frequencies are discretized if you impose some boundary conditions, such as saying that you have a guitar string of a fixed length. Okay. So for a wave on a string, you could imagine a variable which is the height of the string away from its equilibrium position as a function of position and time. And this quantity, h, would obey a second-order differential equation relating the spatial and the time derivatives. So this is something that one can derive just from a simple mechanical model of the guitar string, for example, that we're studying. And we are interested in standing wave solutions. In particular, those waves that have a periodic repeating structure, rather than those waves that describe like some propagating water wave or some propagating displacement of the string that will move at some constant velocity. And these are, in fact, the simplest solutions of this wave equation. In particular, there are those where we assume that the solution is separable. So all that means is that h as a function of x and t is just a product of some function of x times some function of t that I've called f and g here. And then if you plug that into the wave equation, you'll see that the second derivative of f, so the left-hand side of the wave equation, will involve a second derivative of f with respect to x, and the right-hand side will involve a second derivative of g with respect to time, so that 1 over f times, just rearranging this equation a little bit and dividing both sides by f times g, we see that 1 over f times the second derivative of f with respect to x is 1 over v squared times 1 over g times the second derivative of g with respect to t squared. And the utility of writing the wave equation this way is that since f is a function of x and not t, the left-hand side of this equation here must be a function of x. And since g is a function of t but not x, the right-hand side must be a function of t but not x. So you have on the left-hand side a function of x, on the right-hand side a function of t. In order for them both to be equal to one another, both sides must be a constant independent of x and t. So let's give that constant a name. Well, we have that 1 over v squared here. That was necessary by dimensional analysis. And so I'll just give that constant a name. I'll call it omega squared. And then this equation is easy to solve. For example, the equation that 1 over f times the second derivative of f with respect to x squared is equal to a constant divided by v squared is easy to solve. This is the standard second-order differential equation whose solutions are sines and cosines. I should make one comment here, which is that I've called the constant that appears in this equation of motion omega squared because I'm going to take this constant to be positive. One could also try and think about cases where this is negative, but for the case of a wave on a string, those solutions are not relevant. They would correspond, well, we'll see in a second what they would correspond to. Was that your question?
My question is just, is v a constant?
V is a constant, okay. V is, remember from last time, the velocity of a wave that propagates on the string. Of course, one could consider a more complicated wave equation, a more complicated medium, where v is not constant. But for the present, for the simple cases that we're studying, we'll take v to be a constant as well. So what is the solution? Well, the easiest solutions to write down are just sines and cosines. So a solution would be something of the form a constant times e to the I omega x over v. Oops, did I make a sign mistake? Yeah, sorry. I'm taking this constant to be negative. I apologize for that. Good. Sorry about that. And you can see that just taking the second derivative of this guy with respect to x will pull down two factors of I omega over v from the exponential, and you'll get that minus omega squared over v squared times f. So here I'm using the complex notation for the solutions of the wave equation. And for example, if you wanted to write down a real solution to the wave equation, you could just take f to be the real part of a e to the I omega x over v, which would be equal to, for example, some linear combination of sines and cosines of the sort that we considered last time. So for example, if A is real, then that implies that the real part of A e to the I omega x over V is equal to A times cosine omega x over V. Whereas if A is complex, so if A is equal to, say, let's call it the absolute value of A times some phase e to the I phi, then that would tell us that the real part of A e to the I omega x over V is equal to A cosine omega x over V minus phi. Sorry, plus phi. Just using the fact that the real part of e to the I theta is equal to cosine of theta for any real number theta. And likewise for G, G would have a complex solution that's given by some complex constant, which is just a constant of integration, times e to the I omega t. And this then explains why it is that I chose omega as my the name for my parameter. It's exactly the same as a frequency. So for example, the real part of B e to the I omega t would be, sorry, there's an absolute value there, the absolute value of B times cosine omega t plus theta if we take B to be some complex number whose phase is equal to theta. So these are the solutions for the standing waves. So let's now consider a wave, that is to say, a standing wave solution on a string of length L. Where we fix the endpoints of the string so that the value of h at either endpoint of the string is equal to 0. So if you have some guitar string and h is the height of the guitar string away from the equilibrium point, then L is just literally the length of the guitar string between the total length of the guitar string. And this boundary condition that we're imposing, that on either side of the guitar string at either endpoint h is equal to 0, will lead to some constraint on the solutions of this differential equation. So in particular, let's consider a solution. So I could write it either as a cosine or a sine, but let's consider a solution written as a sine. So remember that sines and cosines are just related by a shift of the argument by 2 pi. So just by adjusting that phase phi that appears here, I could write this just as well as a sine instead of a cosine. So let's just write down that solution. So f would be some real number that I called the absolute value of A times sine omega x over V. So that would be one particular choice of solution of this wave equation describing standing waves. And you can see that I've chosen a sine instead of a cosine because this has automatically f equals to 0 at x equals to 0, just because sine of 0 is equal to 0. And imposing f equals to 0 at x equals to L tells us that when x is equal to L, the argument of the sine here has to be an integer multiple of pi, because sine of an integer times pi is equal to 0. So that tells us that x omega x divided by V has to be equal to an integer times pi. Omega L divided by V has to be an integer multiple of pi. So that we see, as promised, the frequencies are quantized. Sorry, I should say discretized. I haven't used the word quantized yet. But the frequencies are discretized. And this is exactly what we discussed last time a little bit heuristically when we talked about a standing wave on a guitar string. And this discretization rule is very, very easy to understand geometrically. If instead of talking about the frequency, omega, we talk about the wavelength, which I remind you is v divided by omega, and that will just be equal to L over n. So the rule that one uses for describing the discretization of frequencies, or the discretization of the solutions to a wave equation for a wave on a string, is the statement that the length of the string is an integer multiple of the wavelength. So that you have this picture. If you have two endpoints here, then when n is equal to 1, you would have something like this. When n is equal to 2, you would have something like that, and so on and so forth. Can I do 3? No. I'm not very good at drawing. Sorry about that. Well, I did it last time. You guys know more or less what I mean. Okay, that's such an ugly picture. Okay, are there any questions on this? This should not be something terribly surprising or new to you. Yes, question.
Did you drop a pi?
Probably. Probably, yes. There's a pi here. And remember that actually, I suppose I should have a 2 pi there, right? Because, yeah, did I drop a pi? I did drop a pi. Here, let's put this n times 2 pi. Or no, we can say pi. And then you'll have a pi here. And then remember that this omega is the frequency. Yeah, sorry about that. Omega, we usually call omega the angular frequency, and f the dimensionless frequency. And so it's just a matter of conventions. Okay. We have 2n here. We have 2n there. Okay. So the length, the conclusion is the same, that the length is an integer multiple of the wavelength. Depending on whether it's an even integer or it's allowed to be an odd integer depends on the type of system that you're studying. Yeah. So remember that, what is it, omega is 2 pi times f, is that right? If you want the thing measured in radians, or yes, instead of in. So we distinguish between the frequency and the angular frequency. Sorry, yes, so I dropped the factor of pi as the answer to your question. Yes. Any other questions? Good. Sorry about that, yeah. Okay. So here's a prediction. The electrons inside an atom are standing waves. And hence, their frequencies and energies should take discrete values. And in this context, we say that they should be quantized. According to this rule, that the length of the trajectory of an electron should be an integer multiple of the wavelength. indeed, one of the most striking observations of that came out of the studies of radioactivity in the early 20th century was that the energy levels that the radiation from various sorts of atoms, various gases made up of atoms, exhibits properties that are indeed precisely analogous to this. So, for example, radiation from hydrogen obeys what's called the Rydberg discretization rule, so that the inverse wavelength, the frequency of light that is emitted from hydrogen, appears only at certain special discrete values of the frequency. In particular, it goes like 1 over the square of some sort of integer times a constant, which is known as the Rydberg constant. So that one would predict that the energy levels, for example, of an electron in a hydrogen atom should be quantized. In particular, the energy is proportional to the frequency or the inverse wavelength. So the energy levels should be proportional to 1 over n squared, where n is some integer. Just to recap, the model that we have in mind is that an atom consists of an electron going around a nucleus. And if electrons are waves, then we would predict that the allowed energy levels of the electron should be discretized in some way. And if the radiation from hydrogen or for some other atom comes because the electron is making transitions between these different energy levels, then that means that the frequency should be equal to some differences between some discrete energy levels. And indeed, it was phenomenologically observed in the early part of the 20th century that that is precisely what the structure of the spectrum of hydrogen looks like. So there's certain discrete lines there's certain discrete lines in the spectrum of hydrogen, that is to say certain discrete frequencies that are preferentially frequencies of light that are emitted by hydrogen gas at some temperature. And this leads to a guess for what the quantization of the energy levels of hydrogen should look like. And indeed, this will allow us to precisely guess exactly what the wave function or what the wave equation obeyed by an electron should be. Yes?
We talk about electron inside an atom are sending waves.
Yes.
So you can show like the amplitude of this wave is 0 and infinity.
Yes. We'll get to that. We'll discuss that. Yes.
So air is infinity?
Sorry.
So air is infinity?
Air? What?
Is
Sorry.
length just like a string?
Yeah. No. We'll get to exactly what that length is going to be like. Okay. So, in order to develop a slightly more quantitative picture of exactly how this discretization of the energy levels of an atom occurs, I'd like to introduce a very simple model for how this works due to Bohr. And Bohr basically postulated, based on these observations, that electrons exist only in certain allowed energy levels, and the rule that he gave for deciding which energy levels are allowed is that the electrons travel in circular orbits, but not just any circular orbit is allowed. In particular, the angular momentum of the circular orbit is quantized in units of h bar. So h bar being Planck's constant h divided by 2 pi, and n being an integer. So indeed, what we're going to see is that this rule, which Bohr just guessed, based on the observation of the spectrum of hydrogen, is in fact exactly the same as the discretization of the frequencies or the wavelengths of a string, a standing wave, on an interval of length L. So first, I'd like to work out the consequences of this quantization rule introduced by Bohr and show you that it's exactly the same as the discretization of the energy levels that or the frequencies that one expects for a wave on a string. So let's consider then our model of an atom. So we have some nucleus here, and we have an electron in a circular orbit around that nucleus. And so that electron will be moving at some velocity v around the nucleus, and it will be subject to some forces. And in order for this electron to move on a circular orbit, the force of attraction to the nucleus, due to its electric attraction to the protons in the nucleus, must be canceled by the centrifugal force due to the electron as it moves in the circular orbit. So the force due to the presence of protons in the nucleus will be proportional to 1 over the radius of the orbit, with a constant of proportionality, c, that is proportional to the charge of the nucleus and this should be equal to the centripetal force due to the fact that we have an electron going in a circular orbit. So that should be equal to mv squared over r, which is the centrifugal force. Sorry, I'm not writing very clearly today. So that tells us that mv squared is equal to c over r, or that v is equal to the square root of c divided by mr. So this is just the relationship between the velocity and the radius of some object that's moving in a circular orbit in a 1 over r squared potential. For example, one could also be studying the orbits of the planets around the sun here, and we would call this due to gravitational attraction rather than electromagnetic interaction, and this would be just as true. And Bohr's rule says that the angular momentum J, what is that? Well, that's mvr. This is just the angular momentum of an object moving in a circular orbit, has to be n times an integer, or an integer times h bar, so that plugging this all in, v has to be equal to nh bar divided by mr, or plugging that into this equation up here, we see that v squared, which is n h bar over mr squared, has to be equal to c over mr, or r has to be equal to n squared, just solving this equation, moving the r squared onto the right-hand side of this equation. R is equal to n squared h bar squared divided by mc. and plugging that into our equation for V up here, V has to be equal to C divided by NH bar. So this rule that was postulated by Bohr says that the allowed radii of the electron moving around a proton should be quantized in this manner. In particular, the radii should be proportional to n squared. And the total energy of the electron is 1/2 mv squared minus c over r. Can be computed just by plugging into this set of formulas in the box here, and that's minus 1/2 mc squared divided by h bar squared n squared. That's just a little bit of elementary algebra. So in particular, we see that the energies, the allowed energies, are at certain discrete levels, which are proportional to 1/n squared, and also proportional to the square of the charge of the nucleus. So you can see that this picture of Bohr actually leads to another prediction. So in particular, in addition to saying that the energy levels go like 1/n squared, they tell us that the coefficient in front of 1/n squared goes like the square of the charge of the nucleus. So for example, if you compare the energy levels of hydrogen to that of helium, then you should expect that they would differ by a factor of 4, because the charge of helium differs by 2 from that of hydrogen. And indeed, this is a result which, as you can imagine, has been verified experimentally to a great deal of accuracy. The point that I would really like to emphasize, however, is that this quantization is the same as that of a wave, a standing wave on a string of finite length. So let's understand exactly how that works. So let's remember that the wavelength of an electron, as predicted, as understood, for example, based on the double slit experiment, is given by the de Broglie formula, that the wavelength is Planck's constant divided by p. So let us just go and compute that for an electron in one of Bohr's orbits. So that's lambda divided by mv. mv just being mc divided by nh bar. So that's h times nh bar divided by cm, just using this formula right here. And remembering that h bar is h divided by 2 pi, we can write this as lambda is equal to 2 pi h bar squared n over mc, or 2 pi divided by n times h bar squared n squared over mc. And what is h bar squared n squared over mc? Well, if my screen were a little bigger, then I wouldn't have to scroll up to show you that it's precisely the radius of the orbit. So that's 2 pi over n times the radius of the orbit. Or, to state this slightly differently, 2 pi r is n lambda. So what does that mean? That means that Bohr's rule can also be stated a slightly different way. It can be stated as the statement that the circumference of the orbit is a multiple of the wavelength of the electron. So when we thought about our guitar string and the discretization of its energy levels, we were thinking about a straight guitar string. But I could have just as easily curved that guitar string into a loop and then studied the waves that live on that loop of guitar string. And indeed, we would have found exactly that same quantization condition. Except it would have actually differed by a factor of 2, which was the factor of 2 that appeared up here. So actually, that would be a fun exercise. I haven't written your problem set for next week. Maybe I'll put that on the problem set. But what we see here is that the quantization rule for the allowed energy levels of a hydrogen atom is precisely in accord with the picture of an electron as a wave that we developed in our study of the double slit experiment. Yes, question?
So with the idea of a guitar string in a loop, would we fix it at one point to have the boundary conditions?
If you want to study a guitar string on a loop, okay. So let's consider the case of a guitar string on a loop. So you have this wave function, this function h of x and t. Then the statement that the guitar string is on a loop is the statement that h at x equals 0 is equal to h at x equals to L. That's all one has to do in order to put this thing on a loop. Okay, one could also worry about the fact that the guitar string is curved as leading to some changes in the wave equation. This is where the analogy between an electron moving moving around an atom and a wave on a string breaks down, and where it's not completely precise. For example, it would be a fun exercise just to solve for the standing wave solutions of a guitar string obeying this boundary condition. Now, for a guitar string, this is not that stretched straight. This is not a very natural boundary condition. Okay, it would. I mean, if our universe were a torus, and if our guitar string were the size of the universe, or if our universe were a sphere and the guitar string were the size of the universe, then it would be a natural model for it. But for normal guitar strings, this is not a sort of boundary condition that we would naturally impose. So for example, given this, well, you would have a quantization rule for the frequencies, in particular that the wavelength would be, that the size L would be an integer multiple of the wavelength. There's a factor of 2 that appeared earlier when I fixed both boundaries to be equal to 0, but only setting them equal to one another, you'll get precisely this quantization rule. So what does this mean? I mean, physically, how should we think about this? So the way that you should think about one of these allowed energy levels is that you have this electron that is orbiting a nucleus, and it's described by a wave, and the discrete radii of the electron that are allowed are precisely those where, if you think about the electron as going around, as describing some wave that is going around this nucleus, then the wave will come back to itself as it goes exactly one time around the nucleus. So that, for example, what have I drawn here? What I've drawn here is my picture where I have a wave on a string, but I've looped it around and connected this endpoint with that endpoint. So you think of the allowed energy levels of an electron as being a wave that's moving around the nucleus, and it has a number of nodes which is equal to that integer n. So n is equal to the number of nodes of the wave. Now, what does this mean physically? Oh, actually it's 1:30. So I'll tell you what it means physically next time. Unless, is there one? Well, maybe I should not. I'll take questions afterwards. Okay, I'll see you guys on Wednesday.